Some of the main features of SwarmJS include the ability to change the current scene, to reset the simulation, to pause or unpause the simulation. The gear icon brings up a wider set of configuration options. In the rendering tab, for example, we can change the number of time steps in between renders, which allows us to see the long-term behavior of the simulation much more easily. We can also control what scene elements are rendered. For example, I could turn off rendering of the robots themselves, and then we just see the sensors themselves floating around. In the Configuration tab, we can dynamically change the number of robots and see how that improves performance or impacts on performance. Some changes require the scene to be reset. For example, if I change the size or the radius of the robots, I'll need to hit the reset button up here to see that change take place. The Benchmark tab allows us to perform experiments directly within the browser. So we can hit Start Benchmark and then look down and we can see a plot updated live of the performance of this system under two different parameter settings. So this parameter called theta here, its value being 0.001 corresponds to the green traces, 0.01 corresponds to the blue traces. So we see the individual trials and we see the average performance of these trials as a heavy trace. And then we can immediately get feedback as to which of these parameter settings might be the most useful. The Controller tab provides one of the most useful features of SwarmJS. It provides an in-browser editor in two components, the first being an initialize function and the second being a function that's executed in every loop of the simulation. So we can make direct changes here that impact the behavior of these robots. So I can, for example, change the forward speed of these robots. Let's just slow them down dramatically. I click this Deploy Code button, and it resets the simulation, and now the robots are driving along quite slowly. Now, if I restore the normal behavior of the simulation and hit Deploy again, and if we hit this button up here at the top to increase the rendering speed, you see that the robots cluster these pucks together, but they also cluster themselves together. So restoring to a single render per time step, you see that the robots are grouped together, which is fine in simulation, but would not work very well in a real world situation. So let's see if we can address this. So I'll come down here and I'm going to make some direct changes in the code. I've made the changes I wanted, and now I have to hit the deploy button. Notice the code is compiled successfully. Now, if I again accelerate this simulation by increasing the number of steps per render, you see that these robots are now maintaining a distance between themselves. Go back to single render per time step, and you can see that now they've done a very effective job of clustering these pucks, and they're keeping distant from each other. So I can click on any of these robots here, And you'll notice this automatically pauses the simulation, and then I can reposition that robot somewhere else, release it, and simulation continues. This can often be done a little bit more easily if we pause the simulation itself and then position robots or other objects within the scene. The physics engine will resolve these collisions between the robots quite quickly. The other thing this scene demonstrates is scalar fields, which are, in this case, projected beneath the robots and which the robots can modify and sense. We can switch between the scalar field representing pheromones and a scalar field called occupancy, which basically shows the positions in space which the robots have occupied.